Okay, so welcome back, and we're looking today at entropy of the surroundings. We left the last video at the end of the entropy of the system. Now the system dealt with the chemicals, so were they gaining or losing in entropy. So when we said we were going from a solid to a gas, we said that was an increase in entropy because we were going from the more ordered state of a lattice where the particles are fixed in position to the more random arrangement of a gas. So we say that's an increase in the entropy because there's just simply more ways that I can arrange the gas molecules than I can the solid particles. So that was an increase in entropy. Also, if I had more moles of products than I had of reactants, that again would be an increase in entropy because I would simply have more things, if you like, to arrange. And the more things you have, the more ways you can arrange them. In this section, we're going to be looking specifically at the entropy of the surroundings. So that's what's happening to everything around the chemicals. So we're looking basically at whether we've got an exothermic or an endothermic reaction. So you're going to need your notes, you'll need a pen, and you're going to need a calculator. Okay, so we should be on page 9 of your notes. And we're looking at these entropy of surroundings. We call it delta S surroundings. So not all molecules have the same energy. They're spread out amongst various energy levels. So for an exothermic reaction, where the surroundings are heating up, they must be gaining entropy. So we're going to go gaining entropy. Because simply we just got more quanta. Okay, so you've got more packets of energy to play with, so you're going to gain in entropy. Now you might have seen this Maxwell-Boltzmann distribution at GCSE. You're certainly going to study it more at A level. So we're going to study this in more detail when we come to the kinetics pack. But for the moment, we just need to know generally that a warmer sample has a bigger spread of energies than a cold sample. You can see that here, this peak here is much higher, but it's also much further to the left. Whereas this warmer sample, there's a lower peak, but the energies are more spread out. Okay, so that's the difference between cold and a warm sample. So the higher the temperature level, the more spread of energy we can get. So that's a higher temperature gives me more ways that I can arrange things. So at higher temperatures, they have not only more packets of quanta, but also they have available a greater range of energies. Okay, so the entropy is a measurement of two things. First is that random dispersal of molecules, and secondly is the energy quanta that is shared. Now, although your exam board accept energy is a measurement of disorder, and it's a good enough tool, it's not something I personally like. I prefer to think of entropy as the number of ways that the microstates can exist in. Okay, so just the number of ways that we can get things. Okay. Okay, so we should be on the top of page 10. So we're looking at calculations of delta S surroundings. So as we've seen, delta S surroundings is known as the enthalpy term, and it's directly proportional to minus the enthalpy change of the reaction. Okay, so we have this little equation, and you're going to have to learn it. So delta S surroundings is equal to minus delta H over T. So delta H is our enthalpy term, delta S surroundings are our entropy term, and temperature is, obviously temperature in Kelvin. Now you need to be very, very careful with units on this one. Delta S surroundings is an entropy term, and it's given in joules per mole per Kelvin. Delta H, on the other hand, is always given in kilojoules per mole, and the temperature is given obviously in Kelvin. Now you just need to be very, very careful that you always remember to convert your delta H value here from kilojoules into joules, otherwise your numbers won't track. Okay, so I'm going to do the first one for you as an example, and then I'm going to get you to pause the video and have a go at the second one. So here I've just been asked to calculate the delta S surroundings. I've been given the delta H for the reaction, so I'm just going to write out my little formula. Delta S surroundings is equal to minus delta H over T, and so that's equal to minus 704.2 times by 1,000 to change it from kilojoules to joules, and divide by 298. That's my temperature in Kelvin. So I'm going to put those numbers into my calculator, and I should get 2363.08 joules per mole per Kelvin. I can't leave my value like that. It's missing a sign. Must have a sign. Also, this is far too many sig figs. I can probably get away with 4 at a push, but certainly not 6. So I'm going to rewrite this as plus 2360 joules mole to the minus 1, K to the minus 1. And that's my final answer. So what I'd like you to do now is have a pause of the video, and can you have a go at the question at the bottom of page 10? Have a go at question 2. Okay, so we should have that equation now at the bottom of this page. So I'm just going to run very quickly through that example for you again. So again, I've got my delta S surroundings is equal to minus delta H over T, which is equal to minus, a bit straighten up, minus 285.8. There should be a brackets around that, another minus sign. Sorry. All right, start that one again. Start that again. So delta S surroundings is equal to minus delta H over T, is equal to minus, brackets, minus 285.8 times by 1,000 divided by, again, 298. And I should get my answer as plus 959.1 joules per mole per Kelvin. I'd rather have my answer to 3 sig figs, so it's plus 959 joules mole to the minus 1, K to the minus 1. And those are the easiest type that you're going to come across. Right, if we turn over to the next page, these ones are a little bit more complicated because we first of all have to use a Hess cycle to work out the change, and then we can use that to work out our delta S surroundings. So we're looking at this first one. So you should recognise this as the enthalpy of combustion of methane. Okay, and I'm going to construct a Hess cycle, use it to calculate the delta H, delta R for the reaction, and then I'm going to use that to calculate my delta S surroundings. So the first thing I need to do is my little Hess cycle. So I've got methane, CH4 gas, being burnt in oxygen to make carbon dioxide and water. Okay, and that's my enthalpy of combustion reaction. I've been given enthalpy of formation to work this out, so I'm just going to start at the bottom here with my elements. I've got carbon, and I've got oxygen, and I've got hydrogen. Okay, so I've got those elements at the bottom. So I can use these elements and make these, or I can make these. So I've got both arrows pointing upwards. I want to work out this delta H reaction, delta H of combustion. I'm going to call this one delta H1 and this one delta H2, just because I can. I don't need to, but I just like labelling them 1 and 2. It makes life a little bit easier. So we're going to work out what delta H1 is. So delta H1 is equal to 1 lot of methane being formed, which is minus 74.8. So that just equals minus 74.8. And then my delta H2 value, well, I've got 1 carbon dioxide and 2 waters, So I've got 1 carbon dioxide, which is minus 393.5, and 2 lots of water, minus 285.8. Okay. Now, to work out my delta H of reaction across the top, so delta HR is equal to minus my delta H1 value, so minus this value, plus, because I'm going in the same direction as the arrow, plus delta H2. Okay, now if I put all those numbers in my calculator, press all the right buttons correctly, I will get minus 890.3. Remember, this is in kilojoules per mole because I'm dealing with enthalpy changes, and I've been told up here that my units are in kilojoules per mole. But I can now use this to calculate my delta S surroundings. So delta S surroundings is equal to minus delta H over T. So that's minus, brackets, minus 890.3 times by 1,000 divided by 298 Kelvin, because that's the temperature at which we're doing this reaction. And I get that equal to plus 2987 joules per mole per Kelvin. Again, I don't really want to leave it as 4 sig figs. I'd rather have it as 3. So that's 2990 joules moles minus 1 K to the minus 1. Okay, so it's over to you. What I'd like you to do now is pause the video and have a go at the questions on pages 11 and 12. And as you can see here, we've now got question 4. So I've worked out my delta H of reaction, and I've used it to work out my delta S surroundings. This is an exothermic enthalpy term, so this will be a positive entropy change, because if it's an exothermic reaction, the surroundings are gaining energy, so therefore they must be gaining also in entropy. Okay, so if we turn over and we'll have a look at the next page, we've got question 5, top of the page there. Now this is an interesting one. This is the first time we've had an endothermic reaction. Now in an endothermic reaction, the surroundings are getting cold. So that's given here by a negative change of entropy of the surroundings, because the surroundings are losing entropy. They are becoming more ordered, less disordered, so they have a negative sign there. Okay. Last but not least, number 6 at the bottom, you have a small exothermic reaction, so you're going to get a small positive increase in entropy of the surroundings. Now, very importantly at the bottom, we've got our last bit, which is basically the summary of this section. This is very important. Okay, so delta S surroundings is equal to minus delta H over T. Now, this is the important bit, that for all exothermic reactions, the delta S surroundings will be positive, because in all exothermic reactions, energy is coming out from the system, if you like, into the surroundings. So it's going to give the surroundings a higher entropy. They're going to become more disordered. Likewise, for endothermic reactions, it is always negative, because the surroundings are losing energy to the system. So therefore, they must be becoming more ordered, colder, if you like. They might even change state into a solid. Okay, so you've got these two things: exothermic reactions where it's always positive, and endothermic reactions where it's always negative. Now, one last thing about this term here. The surroundings, it becomes less and less important as temperature increases, because if you think what happens is this becomes a bigger and bigger number. This number here, whether it's positive or negative, will become a smaller and smaller number. So we say at high temperatures, this surroundings term becomes less and less important, and the system starts to dominate. But at low temperatures, it tends to be the surroundings that dominate. Okay, now that's the end of this video. This was looking at the entropy of the surroundings. The previous video was looking at the entropy of the system. So in the next one, we're going to put those two things together, and we're going to be able to calculate the total entropy change, and that will give us whether or not the reaction is feasible or not.